Say that again. So today we're going to start a whole conversation about proportion. And it's in the polynomial chapter. It's really going to have nothing to do with the rest of the polynomials we'll talk about. But it's kind of a standalone topic. You will see it again on your test day. Don't forget to review it. We'll probably show up in the review sheet as a reminder. But there are three kind of proportions we're going to talk about. All right. And you probably heard some of this spoken casually. Like if somebody goes, oh man, there's a direct relationship there, or directly related, or directly proportional. Those kind of proportions are proportions like you might have seen in geometry dealing with similar triangles. Okay? But I could also say things are inversely related, inversely proportional. Like for instance, what if I fixed the area of a rectangle at 20 square inches? So I told you the area had to be 20. Okay, now give me a possible length and width of that. 4 and 5, or 10 and 2. So what, or 20 and 1, and we're just talking about whole numbers, right? I could have 3 and 27ths. 3 and 23rds, right? I could have a half and 40. But bottom line, what happens as the lengths increase? The widths decrease. Those are inversely related. Okay? If I'm dealing with directly proportional, as I'm saying something like, hey, the fraction, how many ways can you write the fraction 0.5? Yeah, 1/2, 2/4, 3/6. I can go all day, right? 1.5 thirds. So on all of these values are directly related. If I'm doing an inverse relationship, I'm talking about something like area, like we just talked about. Could be 1 and 20, could be 2 and 10, could be 4 and 5, or 5 and 4. Could also be 3 and 23rds. Are you seeing these? So these kind of relationships exist, and they exist all over the place. And then there's another one called jointly that I'll get into in a second. When things are jointly related, it's like you're directly related to more than one thing. All right, and that's true too in a lot of situations. All right, so bottom line, we're going to look at how this works out, but there's a couple things you need to understand. When you're dealing with direct or inverse or jointly relationships, there's a constant of that proportion. And they call it K usually, and it means it's the constant of proportionality. What are all of these things equal to? 0.5. That would be the K value. And the number on the top and the bottom, that X and that Y, or that X and that Y, or that X and that Y, these are all how X and Y are directly related to each other. And as one goes up, the other one has to go up to meet it in some way that would keep the constant of proportionality the same. Are y'all seeing that? Now, this is directly related. And then I'm going to show you the math of this. That's a directly related or a direct proportion, a direct variation. All right, there's all kinds of words, but the key is that word direct. So when you see directly related, either one or two things are going to happen. One, they're going to tell you that X and Y are directly related, and you're going to go, oh, if X and Y are directly related, then that's true. And what you'd probably be given is 3 of the 4 variables. And they'd say, find the missing one that would make that true. So let's just say I gave you a certain X that goes with a certain Y, and then I gave you a certain Y, but not the X that goes with it. And I said, hey, what X would go with that if they were directly related? And you just plug them in your formula and solve for X. Another thing I could do is say, hey, if you have a relationship between X and Y that it's a direct proportion, and X is 3 and Y is 6 or whatever, what's the constant of proportionality? And in that case, you'd be finding what the constant is. Plugging in the X and Y and solving for K. So these things aren't overly difficult. You'll see that when we do examples. Pretty basic, actually. And you'll even do word problems with these, and the word problems will look horrible. And you know, I don't know if you remember in my other room, probably not, maybe though. There was a little picture of a guy yelling at a dog. Oh yeah, the little Far Side one. And it's like maybe I've mentioned that before, but it's like I use it to talk about how we read word problems. We read like a dog. Because like a dog sitting there and you're like, bad dog, I forget what the dog's name is. Bad dog, Lucy, blah, 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 stay out of the garbage or else, blah, blah, blah. And he's yelling at the dog and says, what a dog hears. And it's just blah, 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 Lucy, blah, 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 blah. Because they just put on little pieces. And that's generally not the way to read a word problem, right? Reading it, blah, 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 27, blah, 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 6. I don't know what to do with this. Well, man, you can do it on this. Now you can go, so-and-so is blah, 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 directly, blah, 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 so-and-so is blah. And literally it just flows off the page and they're telling you what to do. And you might not even understand what a capacitor or velocity or power or all these different variables, they may not make any sense, but man, you can do these word problems if you just clue in to what they're telling you is directly, what they're telling you is indirectly related, and we'll do a couple of those examples as well. All right, so directly, remember, you're basically setting up this expression. All of your xy's would be written in fraction form, and they're all equal to some constant. And you may or may not even need to know that constant, but it's there. Whatever the two fractions are have to be equal to each other, hence that constant proportionality. If you see that word directly related, directly proportional, direct variation, that's the setup. Now, inverse. Inverse is this one. On an inverse, the constant of proportionality would be a product of two things. Right here, that 20, which every one of these is equal to, that would be my k value, my constant of proportionality. And you'd have a setup like, well, some x1 times some y1, or some x2 times some y2. They're all equal. And if they're all equal, and I only gave you 3 of the 4 values, you could set up that equation. But each product is always equal to that constant. And you're looking for the word inversely, if I said directly, sorry, inversely proportional, or an inverse proportional, or they might say inverse variation. But you're looking for that keyword inverse. So if you see that keyword inverse, you immediately go, oh, xy, xy, plug and chug. Now, there was one exception. Sometimes I don't say things like x and y are inversely proportional. Sometimes I'll say things like the square of x and the cubed root of y are inversely proportional. And you set up like that. And you say, oh, if the square of x and the cubed root of y are inversely proportional, then x1, y1, x2, y2, those would have to be equal. And what is the product of this equal to? K. All these would be equal to some constant. But most of the time in this course and in math team permits, you're going to be working with this. And you'll be given 3 of those 4 x values. You'll see this. This is not going to be difficult. You'll be given 3 of those 4 x values, and you just plug in the ones you know, and you solve for the missing one using the algebra you already have. And it usually is not over. The biggest mistakes I see on this are when I say things like the square of x, people write square root. But the square of something is you're squaring it, right? And the square root, you'd be rooting it. You with me? Riveting stuff. Okay, jointly related. Jointly is a variation that's like directly, but instead of x being directly related to y, it would be directly related to y and z. So on a joint variation, I'm going to get rid of all this. And then we're just going to do random problems until we are sick of them. Well, you may be sick of them now. We'll do random problems until we're done with time. So jointly related, or a joint variation, would be something that's jointly related to 2 other things. So if I said something like x is jointly related to y and z, or to both y and z, the joint relationship says x is directly with y and directly with z. Basically, you're dividing by both if it's directly. Don't do two separate problems. Every year somebody tries that. They go, jointly means directly with both. So they go x over y equals x over y, and then they go x over z equals x over z. Don't do that. It means x over both y and z. So you'd go x over yz, x over yz. You'd set your first grouping of x, y, z's, your second grouping of x, y, z's in there. You set them equal to each other, and that would be that kind of proportion. And what are each of these equal to? To what? K. Because they all share that same constant of proportionality. And by the way, that constant of proportionality would be unique to a certain problem, but it will vary from one problem to the next. Like, have y'all ever heard of half-life decay or half-life carbon-14 dating, stuff like that? Those kind of things measure like the how old something is, because they figure, hey, I found this ancient leaf. You know, leaves are supposed to have so much carbon, but over time, their carbon decreases the amount in there. So if they measure the amount of carbon in this fossilized leaf, they can use the whole idea of, hey, I know how long it takes for carbon to decrease, and I can approximate what that age is. Well, that's kind of like half-life decay. You figure out what the half-life is, and you'll have a certain K value for that. And you see this K value show up in calculus, exponential growth, anything shows up all the time. In calculus, we do a lot with that, with Newton's law of cooling. All these things sound really bizarre when we're doing them, but when you get to calculus, you're like, man, so much easier than my last 2 years of math. All of my AB students that I had in this class that ended up bailing and going to regular pre-cal because they had C's or D's, whatever, they have A's or B's. All the ones who hung out the whole way and had C's or really low B's, they have A's. I mean, AP Cal is not harder than these classes. You really probably should get a higher grade point in this class and in the pre-cal than you do in AP. But Homewood won't let me. I mean, I've fought for years. I only kind of gave up fighting, but they used to not even get a weighted point. I know, you do all this extra work and you got nothing for this class or for the other class. It wasn't until probably 10 years ago, 8 or 10 years ago, that they finally relented and gave a half a quality point. And I think it was because everybody else everywhere, Vestavia, Mountain Brook, they were doing it. And they were like, I mean, even at Hoover, they give a 0.5 for pre-AP and a 0.75 for math team pre-AP. And they won't do it. But I think they finally did give you something just to kind of keep people from going, screw that, I'm not taking that class, killing my GPA or whatever. Which it still might a little bit, but at least it lessens the pain. Y'all with me? All right, so those are your three kinds of joint variations. So let me just throw some problems at you, and you'll see, as long as you read, and you got to read the problem, but you'll see that as I'm reading the problem, it's really not that hard to set it up, to plug in numbers, and you'll see that this is not going to be an overly huge deal. So what about this? You tell me how to set it up and what to do. Again, I think you guys will like this. Most people do really well on the couple problems you might see on the test. So what if I said, if the square root of x varies directly as y squared, and if x is 9 when y is 4, what is x when y is 2? Can y'all see that? My marker's dying on me. All right, so what jumps out at you?
Directly.
Directly. And what do we do with directly? X over y. So, but it's not x over y, it's the square root of x over what it's directly related to, which would be the y squared. And then I'm going to write it twice. Didn't mention anything about a constant of proportionality, right? So I don't need to put k in the equation. But these are going to be equal. The only thing you need to do here is to show, if you wrote that formula out, to show that they are different x's, we just put 1, 1, 2, 2. That doesn't do anything but just to and y is 4 squared.
Wait, why? Oh, sorry, I thought it was a greater than.
Sorry, equal. What is x? So leave the x in that part when y is 2 squared. I'll just write it as 2 squared. Then you just got to clean it up. So 3 over 16 equals root x over 4. And what would you do to solve this? You could. That's going to put the 16 over there with the root x, which now you're going to have to get rid of. What would be even better?
Square of the right.
Well, you could multiply by a 4, gets rid of that 4, and reduces that to 4. And then now when I square both sides, it might be a little bit easier, smaller numbers, right? So all I have left is a 3/4 equals root x, and I square both sides, and what do I end up with for x?
3.
9/16. So x is 9/16. And when I plug 9/16 back in here, and I simplify both those sides, I should get 3/16 on both, which is my what? K value, my constant of proportionality, because it's the same thing every single time. What if I change this to inversely? What changes? Yeah. So the only thing that changes here in the setup is I'd have times y squared times y squared. So what do? Same process, right? When x is 9, root 9, y is 4 squared. When x, what is x? Root x. When y is 2 squared. Same process though. 3 times 16 is 48 equals 4 root x. All right? Divide by 4. Square both sides. Great. I mean, again, there's really not a whole lot to this kind of stuff. Just not. How about this? Throw a curveball at you. You can handle it. What if I said, suppose R varies directly with S and inversely with the square of t. If R is 2, S is 3, and T is 4, then what is T when R is 3 and S is 6? Well, what do you see? Let's slow it down. R varies directly with S. What is that saying? R would have to be over the S to be directly with it, right? But it also says what?
R times T.
Inversely with the square of T.
RT squared.
So times the T squared. So R is directly with S, inversely with the T squared. Doesn't say anything about the constant. So R1, T1, S1, R2, T2 squared, S2. And I set up that equation, and I'm just going to plug and chug, and hopefully I won't make any algebra mistakes. So if R is 2, when S is 3, and T is 4, which would give me 4 squared, 16, then what is T? Leave the T squared in there. When R is 3 and S is 6. Hey, have I ever talked to y'all about the slide rule? Okay, the slide rule, don't get that confused at all with an actual slide rule, which if you've ever watched a movie like Apollo 13 or something like that, they're literally using this before everybody had calculators, and it was a really cool little instrument. I don't even know how they work. I'm sure you could Google it or YouTube video or whatever, how it actually operates. But they would use it to do calculations, real complex calculations too. It was a pretty cool little creation. Now it's a relic that old engineers have like on their mantle or
Oh, the thing where you like
bookshelf.
slide the pieces over?
No, it's not an abacus. You're going way back now, right? But no, that slide rule, I don't even know what they look like, honestly. I mean, if I saw one, I'd go, okay, that's a slide. But I couldn't describe it to you off the top of my head. But anyway, what I call the slide rule is a little algebraic manipulation that really is just algebra. But this is what I'm saying. Like in expressions like x over y equals x over y, you know, we get in situations sometimes where we get fractions like this. Are you with me? Now think for a second. If I multiply both sides by a 6, where does that 6 end up? Where? Up here, because it cancels there, right? So I could have just slid the 6 up. If I multiply both sides by that 3, what happens? The 3 cancels there and ends up being over here, right? So I could slide that up. How about this? If I wanted to divide by both sides by a 3, divide by 3, divide by 3, the 3 cancels over. What does the 3 end up? Down here. If I wanted to divide both sides by a 16, divided by 16, divided by 16, where does the 16 end up? Down there. What this means is, this is my little slide rule, in an effort to simplify the whole process of the algebra, like if you go back, well, forget it here because this is not a fraction equal to fraction, but if you have a fraction equal to a fraction and nothing else, no other junk added to it or whatever, then what you can do is, if you want to get rid of numbers to solve for a t, anything in the numerator, slide down to the denominator, anything in the denominator, slide up to the numerator. And that works for anything. Like for instance, if you had something like 5 over x equals 2 over 3, and I want to solve for x, you could slide the x up, slide the 2 down, slide the 3 up. Check it out. Slide the x up, slide the 2 down, slide the 3 up. There's your x, 15/2. And you don't have to write as much junk. So right here, if I want to solve for t squared, what can I do? Slide the 6 up, slide the 3 down, and you got your t squared. It's the same math, guys, as this, isn't it? Think about it. Isn't it the same math as multiplying both sides by a 6, dividing both sides by a 3? Same thing, right? It's just a lame little slide rule. And I kind of find it useful when I'm trying to simplify quickly. So I end up with this thing, right? So I can cancel a little bit. That 3 and that 6 gives me a 2. And I end up with 4 times 16, which is 64 thirds, equals t squared. So what would the last thing I do be? And if I square root both sides, what do I get? T equals positive or negative what? 8 over root 3. And what is 8 over root 3?
8 root 3.
8 root 3 over 3. So if you want to use the slide rule to save yourself a moment, and we're talking not much, but a little bit, remember, fraction equal to fraction. All it is the algebra, just simplified into a little trick. Y'all seeing this? I want to give you one more jointly.
Wait, you said something about constants. Could you do one of that?
Oh, so if I said, what is the constant of proportionality in this situation? Well, the constant of proportionality will be whatever these fractions or whatever these products are. So all you have to do is go back to what I had, right? And wouldn't the constant of proportionality just be 32 thirds?
Yep.
It's whatever each fraction standing alone would be. once I plug my t back in here, that'll give me 32/3 too, but I don't really want to square that and then multiply it by 3 divided by 6. I'd rather just use the one that I already have the values for. Are you seeing this? Okay, I'm going to change this problem a little bit. Suppose R varies jointly with S and the square of t. So same thing, but R varies jointly with S and the square root of t. So how do I write that? R varies jointly, so it's directly with both. Now don't put the 2 on the bottom and add them because you see the word and, right? It's directly with both, so both go down on the bottom as a product. So jointly with S and square of t, so t squared. You with me? So there's the first set, there's the second, set, and then plug and chug. If R is 2, when S is 3 and T is 4, so 4 squared 16, then what is T down there on the bottom when R is 3 and S is 6? Now, using your slide rule, could you do it? Where do you want the T to end up?
On the right.
On the top. So you could just flip both sides if you wanted to, but using your slide rule, you could slide the T squared up. Then what? Slide the 2 down. The 3 and the 16 up. Now don't scribble out too much on your test or I can't see what you began with. A lot of times people just scribble everything out and I'm like, I don't see your original formula. I can't tell what you've done if you were wrong. So at this point I get t squared equals, a little bit cancels. Actually a lot cancels. And I'm left with 12, 3 times 4. So when I square root both sides at that point, I get t equals plus or minus 2 root 3. Not too bad. Okay, I'm going to pull out my textbook, and I'm going to read a couple of these word problems for you. And you're going to initially go, oh, my Lord, how on earth are we supposed to do this? And then we're going to read like a dog. And when you read like a dog, you'll see, oh, these aren't so bad after all. So we're looking at page 3, probably 61. If you have your book, if you don't, no worries. 361. And we're looking at, oh, yeah. Okay, number 1, I'll read it to you. The frequency of a radio signal varies inversely as the wavelength. A signal of frequency 1200 kilohertz, which might be the frequency of an AM radio station, has a wavelength of 250 meters. What frequency has a signal of wavelength 400 meters? Sounds like a physics problem until you slow down and see frequency, inversely, wavelength. Done. Frequency. Now, I might not know the variable for frequency, but I can certainly write a F to do this problem. So frequency, inversely, what do I do with inversely? Wavelength, L, or W if you want. Frequency, length, 1, 1, 2, 2. And I keep reading. Frequency of 1200, wavelength of 250. What frequency? Wavelength 400. Dude, I don't even remember what I read to you. Are you with me? I mean, these things, you don't have to understand the actual physics of it to be able to do it. How would I solve for F? Divided by 400, 750. Okay, 750, I guess. And if I really want to be fancy, frequency, it said, was measured in kilohertz. Kilohertz. I could just borrow the units. How about this one? By Ohm's law, the current flowing in a wire is inversely proportional to the resistance of the wire. If the current is 5 amperes, when the resistance is 24 ohms, for what resistance will the current be 8 amperes? blah, blah, blah. Current is inversely proportional to resistance. Current, resistance. Plug and check. Are you with me? Let me get something dirty. Okay, the stretch in a wire under a given tension varies directly as the length of the wire and inversely as the square of its diameter. A wire having a length of 2 meters and a diameter of 1.5 millimeters stretches about 1.2 millimeters. If a second wire of the same material and under the same tension has a length of 3 meters and a diameter of 2 millimeters, find the amount of the stretch. Blah, blah, blah. The stretch in a wire varies directly as the length, right? And inversely as the square of the diameter.
Times
Diameter squared. 1, 1, 1. 2, 2, 2. Plug and check. So even these word problems, guys, you read them and you're like, no, can't do that. But it's really, you can read like a dog. You just have to look for the word inversely, jointly, directly. Look at the variables. Sometimes you might have to make up your own variables because it is a word problem. It's not going to spell that out for you. But a lot of them, I mean, stretch, there might be an actual better variable than S for stretch. But again, you're just trying to find the value, so go with it. Y'all seeing that? What do we got? 8 minutes?
No.
Power schools.
Yes!
No.
What kind of question is that?
Optional.
Okay, what are you feeling right now when I say
No.
power school?
Not
It's like your adrenaline start flowing, you get like a pit in your stomach, kind of. It means you're alive, man. Spirit of competition. Now, I'm going to give you a solid 7 minutes back. Enjoy, we don't get that much. Feel free to chat.
Sonny, can you see me?
I was like,
Yes.
I was scouting.
Let me log in. Oh, I think there's a test. Is there,
So you're pretty English. Is it easier than last year?
Yeah, it's easy. I
It's
think
just been done, and I was like, I'm never doing this again, and then I've been doing, everyone's like, it's so easy.
I live in 98. Huh?
This man here.
Yeah, there's a great hobby. It's not exactly working or something. I don't know. I really Okay, Sam. What is Sam, is your air on?
Yeah. Yep, me and Margaret.
What kind of-
I don't know. Okay, it's
It's like a little mini, small SUV. Yeah, SUV, so.
Those are the one I saw a guy.
What?
Wait, was it the Bruce?
Yes.
Had a little-
That's the best they have. That's my
No.
next.
They're making more?
Yeah.
No way.
It's a sweet ride.
Oh, it's awesome.
Yeah,
It's like, it's got a turbo.
Yeah, they always say that.
You can tell, it's also got the coupe shape.
But it's right.
Stick shift.
No.
It's nice. Whenever Marvin is in the car, he likes to drive that one. I don't drive it to school because I'm
Are you there?
all day.
I don't know if you're serious.
I haven't got that.
I was gonna.
Do you drive a manual car?
Yeah.
I don't know.
My
dad- They're fun. My dad's jet to go.
They're fun.
But she also
Live in
knows
like
you're not, right?
a place like this, you're gonna drive these 20 miles.
Yeah. But like in city, it's like in the middle of the city. Yeah. Just going from
Your mom?
When you have to like
the
stop.
whole time.
Yeah.
It does say
Imagine
gas.
stopping at the
My cousins, they live in Bogota and like it's super crowded there and it's up in the mountains and everyone uses it. So, does it save gas?
What can save gas?
It can save gas.
But what really happens if you're a dude and you got a manual shift? You're winding that sucker out, right, and burning more gas.
But they always like, they change gears so quickly. they're in like third going 10 miles per hour. Like they save a lot.
Where is this?
Bogota,
Yeah,
everyone's favorite city.
Ryan,
I've been down to Peru,
Ryan.
and
It's like all over.
it's like
So
NASCAR.
they're actually.
If you're in the major cities, it'll be like 7 lanes wide, but no markings.
Yeah,
For lanes.
it's like that. Egypt is like that. There's no lanes, and there's
And everybody
nobody
sits on
follows.
honks.
Like if it's 3 lanes, there's gonna be 5 cars.
Yeah, and then just honk to let you know I'm speeding past you. Listen, when I went to Peru, we landed in the city, and we left the big, I think it was Lima. We left, went up in the mountains for a week, came back. So I was really only in the city for a grand total of where I actually could see and stuff, 6, 7 hours, maybe. Saw 2 dead guys run over by cars
Oh, my lord.
in 7 hours. Yeah,
Yo,
literally 2 guys. That's how crazy it is. And everybody's walking around on the side of the road with a bundle of something. It's chaos. It's like NASCAR. They say, and nobody even turns around. And if you don't,
Where is this?
this is Peru. It's crazy. I mean, everybody's just, I mean, it's nuts.
I almost got hit by a car in London because I looked the wrong way.
Oh, because right.
It's like, it's a one-way street,
You look left.
almost.
Yeah.
My cousin was Santiago in Chile. And he was a motorcycle because he was a motorcycle. He was just like.
Yeah, that's bigger than most
Yeah, my
cars.
cousin just has a bike that he uses to get to work. It's like, it takes 2 hours to get anywhere.
Wait, Isaac, is it another time with like the license rule? It's like on certain days your license like has to end in like an odd number. if you want to drive.
Yeah.
I don't know.
But maybe Costa Rica, there's some places.
I have no idea.
Oh, because of the overcrowding?
Yeah.
Bogota's so crowded that, like, first of all, it's up in the mountains, so someone can expand anywhere. There's no metro, and the streets aren't that wide. I'm pretty sure it's like in the top 3 most crowded here. Traffic congested.
And there's 2 cars parked, and
Yes.
then another car's coming, and they're not slowing down, and you were here first.
Dude, that's like the same on my street, except it's not as wide as Broadway. Get this, Broadway is pretty long. Yeah.
Yeah, like in downtown Edgewood, like it's so annoying. You park on both sides of the road.